We created the Sunulator to help people answer the question, is solar worth it?
Hi, I'm Andrew Redaway from the Alternative Technology Association. This video is on Sunulator, which is our free solar feasibility calculator. To find it and download it, just do an internet search on the word Sunulator. And that brings up our web page, which has quite a lot of information, including a comprehensive user guide. This video is part of a series that covers the material in our standard Sunulator training course, which we've already delivered in several cities in Australia. This one is looking at the model part of Sunulator. So from the introduction sheet, when you open up Sunulator, we just click on the word model on the menu to the left. So the first thing that we need to enter is what state we're interested in. So we just click on the yellow box that relates to the state, click the arrow and choose from the drop down. Yes, I know that the Northern Territory is not actually a state, but close enough. And the ACT is included under New South Wales, by the way. Sorry if that hurts any sensibilities there. Now the next section is about scenarios. So often when you're modeling a solar battery system, you're not just interested in one configuration. Like you may not know exactly what size of solar system you want to put on, which way the panels are going to face, whether you want a battery or not, what sort of tariff you're likely to choose from your grid retailer, all those sorts of variables. So it's often quite useful to be able to run several different scenarios at the same time, which has different values for some of those variables, and compare the results side by side at the end. And that's what the different scenarios allow you to do. So Sunulator allows up to 6 scenarios, so we've got numbers 1 to 6. Each scenario needs a name that you can type in, and also a location. So with the normally you'd have scenario 1 as the business as usual scenario. We normally just give that the name BAU. So that would be what you have as the base scenario that you're going to compare everything else against. And often that is if we're modeling a site with no solar and no batteries on it, then that would be the business as usual scenario. Then your other scenarios would often be with different configurations of solar system and batteries on them. You can call them whatever you want. You could call them eeny, meeny, miny, mo if you wanted to, but the convention that we've found useful is to name them according to the rated capacity of the solar panels. So in this one it's 4 kilowatts for a 4 kilowatt solar system. So just for interest, that's about 16 solar panels perhaps. And then also according to the rated capacity of the battery storage that's included in the system as well. So this one is again a 4 kilowatt solar system, but it's got a 2 kilowatt hour battery included as well. So you can see that these scenarios have been selected to compare the effect of different sizes of batteries included in the solar system. So later on we'll see how that impacts the electricity import and export from the grid, and also the bill savings that might eventuate if you were to put on different sizes of battery, either no battery, a 2 kilowatt hour or a 5 kilowatt hour battery. Now when you're selecting the location, you would have downloaded the Sunulator file from our website and placed it on your computer somewhere. And built into that Sunulator file, which is a Excel file, Microsoft Excel, is a range of locations already built in. So if we click on the drop down, you can see which location options you have available. If you've only downloaded Sunulator and nothing else, you will only have the from Darwin down to Adelaide here, plus Melbourne and Hobart. However, if you've downloaded an additional file, you'll also have all the extra locations, all the regional locations for your state that you've selected up here. So it's available on our website, these supplementary text files to provide the data for all those regional locations. And the only thing you have to remember is to save that text file in the same folder or the same file directory that you saved your Sunulator file. If you're just concerned with the capital city, then you don't need to worry about that supplementary file. The only reason we've done that is to minimize the size of the Sunulator file. It's already a 3 megabyte file, and if we'd included all of the climate data for all of the regional locations, the file size would have been prohibitively large. Okay, so we've selected our state and we've selected some names for our scenarios, identified what location, geographical location they're in. So let's go on to telling Sunulator about what sort of solar system we have for each of those scenarios. In this sheet, we tell Sunulator about the solar system. You'll see that it's broken up into two sections. We've got the first array and the second array. So the solar array is a group of solar panels that's all facing in the same direction. In this example, we've only got one array. You can see there's no numbers in the bottom section. That's perfectly valid. But you can imagine if you had a roof that was one side was facing east and one side was facing west, for example, then you'd want to enter those two sections independently. If you've got a more complex roof which has 3 surfaces all facing different directions or more, then you can't model it explicitly in Sunulator. However, once you get to solar panels spread out over that many different directions, then it's becoming a fairly generically oriented overall array of solar panels anyway. Your generation is going to be spread out fairly widely over the whole sunshine period of the day anyway, and you'll probably get pretty close by just modeling 2 arrays which are pointing in a sort of average directions to cover the overall orientation of all of your panels. So the first row that we've got here is for the rated capacity of the array, and that's in kilowatts. So just to give you an idea, I think the average size for a residential solar installation is about 4 kilowatts. So that's around 16 panels. Maybe if the panels are relatively high power for each panel, then you'd have less than 16 to make up the 4 kilowatts. So that's why we've chosen 4 as an example in our downloaded Sunulator file. We also have an example section here in grey, just to if you'd deleted all of the other data, then that just gives you an idea. So each column is for each scenario that we named in the previous sheet. Business as usual has no solar system, so that's going to be our baseline comparison that we compare the other scenarios against. Then our 4 kilowatt scenario, it's not surprisingly. It's got 4 kilowatts of solar panels rated. The next row is the panel tilt. So that's the degrees above horizontal. So if it's a very flat roof, then that might be a 5 or 10 degree tilt. Normally you'd want the panels to be on at least 10 degrees so that they get washed fairly well by rainfall. If it's more of a traditional kind of peak roof, that might be 20 to 30 degrees. Yeah, and you could have roofs tilted more than that, or of course you could have panels on a tilt frame that tilts them up higher. The orientation is whether they're facing north or east or west, and you can either enter this as a compass bearing or you can just enter in abbreviations. You can type in NE for northeast, for example, or SW for southwest. In Australia, you'll get the maximum generation over a whole year if they're facing north. But yeah, east and west is in some situations it's quite favourable, because east facing array will generate more in the morning when you might have a morning consumption peak, and west facing array conversely would generate more in the evening to match up with an evening consumption peak. The array efficiency, so that's just a overall efficiency number, because you have some losses in the panel itself. You have some losses in the wires. You have some losses in the inverter that converts the direct current from the panels into alternating current for your house or for the grid. So when you add up all those losses together, then a reasonable value would be around 87%. We've done some testing on that against data on self-reported solar generation, and that seems to work quite well. It also matches up reasonably well against other solar calculators. Now, that number does not include temperature derating of the panels. So as a panel heats up from being on a hot roof and in hot sun, it actually its generation electricity output decreases. So your panel would work better on a sunny, cool morning rather than a stinking hot summer day with the same amount of sunshine. I'll come back to that in a minute. Actually, I'll come back to that right now. It's in the advanced section. So I won't go into this in a lot of detail, but in the advanced section are some settings there which allow you to control the temperature derating of your panel if you want to get into that level of detail. You'd be fine to just stick with the default values. So we've told Sunulator what sort of solar system we have on the roof. In this example, it's very simple. All of our 3 scenarios have exactly the same solar system. 4 kilowatts of panels, pointing north, tilted up at 20 degrees, and our overall efficiency is 87%. Through to the electricity that flows into our house or out to the grid. Let's click next. Okay, batteries are a pretty hot topic at the moment. There's a lot of interest in their ability to save excess solar during the day, store it in the battery, and then use that in the evening or the night time to avoid having to import electricity from the grid, or at least minimize the amount of electricity that we have to import from the grid in the evening and night. So this is where we tell Sunulator what sort of battery capability our different scenarios have. So the first row is the rated capacity of the battery. Now, in a business as usual situation, yeah, we've got no battery, it's just blank. and in the 4 kilowatt scenario, that's meant to model just solar panels on the roof but no battery. So we've got that zero or blank has the same effect in Sunulator. Now our 4 kilowatt of solar 2 kilowatt hour batteries, not surprisingly, has 2 kilowatt hours of battery storage, and the 5 kilowatt hour has 5 kilowatt hours of battery storage. So there can be a bit of confusion between the rated capacity and the usable capacity of a battery. So we've got a row for rated capacity and we have a row for usable capacity. Different battery manufacturers rate or advertise their batteries with different types of numbers, different definitions. The rated capacity would normally be the total capacity of the battery, but a portion of that would normally be reserved and unusable, unavailable to the user. So what's left over would be the usable capacity. For example, the Tesla Powerwall, it's been marketed as a 7 kilowatt hour battery, but in fact its usable capacity is 6.4 kilowatt hours. So in Sunulator we've got a facility here for you to explicitly put in the rated capacity and then put in a maximum depth of discharge. So if your battery was marketed with a 5 kilowatt hour rated capacity, but say an 80% depth of discharge, then you put in your 80%, and that works out your usable capacity as 4 kilowatt hours. But if you're if you have available the usable capacity, then you can just enter that straight in the top line and set the maximum depth of discharge as 100%. That's going to have the same effect. The maximum state of charge would be if you do not, if your battery is restricted so that it can't ever be filled up to a fully charged state of 100%. That would be pretty rare. But if you do have a battery like that, then you can set that to say 90% rather than 100. Now the battery chemistry. Batteries are chemical processes, so inside the battery, as you charge it up, you're converting some chemicals into other chemicals, and then as it discharges, it's converting back again. There's a few different chemistries that are on the market now. At the moment, Sunulator has lithium, so that's the favoured choice for grid-connected batteries at the moment. It seems to be what most of the ones coming onto the market are designed as. And it's also got 3 different types of lead-acid batteries: the flooded, the gel, and the AGM lead-acid batteries. We'd like to build in a few other chemistries when we get some funding or some capability to add that, put the programming in to do that. The effect that has in Sunulator by choosing that chemistry is it's a couple of things, but it's mostly related to how the efficiency of the battery will change with the rate that you discharge it at. We'll see in a minute that we're going to enter an efficiency into the battery, but on top of that efficiency, you also have higher losses that can creep in as you start to discharge the energy out of the battery more quickly. That's more of a problem for lead acid rather than lithium batteries. Okay, our next one is the strategy for operating the battery. And if we click the drop down, we've got Solar Buffer Simple or Tariff Optimized. Now, any battery system, it needs to have some smarts built into it, some logic to determine when we're going to be discharging the battery and when we're going to be charging it up. The Solar Buffer Simple works on a logic of, if you're generating more electricity than what you're using in the house or the business, then you've got excess electricity. We don't want to just export that out to the grid because normally you don't get much benefit for that. Excuse me. So we're going to charge up the battery instead. And conversely, if you're generating less than what you're consuming, then we don't want to import that electricity from the grid and pay relatively high rates for it. Instead, we'll source that battery from the we'll source that energy from the battery and by discharging the battery. So that's how the solar buffer simple works. It's basically minimizing your use of the grid. Now, Tariff Optimized, it uses the same logic, but then it adds on some extra rules as well. With the Tariff Optimized, it assumes that your battery system has the ability to import electricity from the grid to charge up the battery. So with the solar buffer simple, it's only ever charging up the battery from the solar panels. With the Tariff Optimized, it'll do that, but it'll also make a decision at the start of every day, so at midnight every day. It'll make a decision on how much electricity it's going to import from the grid to pre-charge the battery. So normally your battery would be discharged, or at least partially discharged from the previous day, and you're going to get some charge coming in to charge up the battery from the solar, but maybe you won't get enough charge coming in to fully charge the battery. You won't get enough to charge up the battery enough to meet your requirements for the evening and the night time. So it may be in your interest, especially if you're on a time of use tariff with cheap electricity in the early hours of the morning, to charge up your battery, pre-charge it with a certain amount of electricity from the grid, to ensure that when you do reach your peak tariff in the afternoon and evening, and the sun's gone down, that you've got enough in the battery to see you through as long as possible, to avoid importing that expensive peak electricity from the grid. So with the Tariff Optimized, it actually makes a simple forecast of how much generation it's expecting that day. It just assumes it's going to generate the same as yesterday, and a forecast of how much consumption you're going to have through the day. It assumes the same as 1 week prior, and it does a pre-simulation to work out how full is the battery going to get through the day, and is it going to has it got some extra room in there to store some electricity by pre-charging from the grid, and would that be helpful later on in the day? So it's making that decision and then saying, okay, right, today we're going to pre-charge 3 kilowatt hours from the grid, for example, and it'll spread that out over the morning peak. So the morning off-peak period. So that might be from midnight to 7 a.m. in the morning, for example. It's not all plain sailing, because obviously that forecast is not always going to be right, especially with the simple rules that are built in at the moment, as I mentioned. And if you pre-charge the battery more than optimum, then you're not going to have enough room in the battery to store all of your excess solar generation during the middle of the day. So you'll end up exporting more of that solar generation out to the grid for little value. On the other hand, if you pre-charge less than optimal from the grid, then you're going to maybe not have your battery charged up enough at the end of the day to supply your electricity consumption during your peak tariff times in the late afternoon, evening and night time. So yeah, if in doubt, just choose solar buffer simple. It's Tariff Optimized is an interesting comparison to just get a feeling for what sort of difference to your bill savings you might get if you have a more capable battery with some more clever smarts built into it. And you also have the option to choose a time of use tariff from your electricity retailer. Initial state of charge is just starting off the simulation. That's not going to affect much. Alright, so the next section is about charging the battery. What's the efficiency? If it's a lithium battery, then you're probably looking at an overall round trip efficiency of 90%, or maybe a bit worse than that. So maybe 88% or something. If it's a lithium battery on a DC coupled, fairly efficient direct way to get electricity from the panels into the battery. So you're losing about 5% to get when you're putting electricity into the battery, and then on the discharging you're going to lose about 5% when you get it back out again. As I said, batteries are a chemical process. You're converting one chemical into another, and you have some losses, some heat losses normally in that process, and you also have electrical losses through the components in your battery system, through resistance in the wires and things. So yeah, unfortunately there's no free lunch. The next section is about the speed of how fast you can get energy into and out of the battery. And there's two ways that we can enter that. We can do it as a number of hours to fully charge the battery. So if your battery is empty and you're charging it at maximum rate, how long will it take to get up to 100% full of your usable capacity? So with a lithium battery, you may be able to do that in 2 hours. That's the sort of time that we're seeing with some of the specs of the current batteries. But there are some that have a much slower rate, so that's something to keep in mind. And if you were comparing two different batteries with different rates of charge and discharge, then you could set up two scenarios where everything else was the same except for that charging rate. The other way that you can express the speed at which you can charge up the battery is as a power rating in kilowatts. So that could be a specification that's on the battery, or on a inverter that's required, or a DC to DC charge converter to get the energy into the battery, and then the same back out again. So there's two different ways, yeah, what Sunulator does is it converts it into a kilowatt rating. Minimum charge kilowatt, I'll skip over that, and that's pretty unlikely to be needed. It's in the manual as well. Now we also have an advanced section for the batteries. I won't go into that in detail, but I'll just give you a quick look. Here you can specify limits on how quickly we can charge and discharge the battery at different times of the day. One thing you might want to use this for is to set block-out times on your battery. For example, if you had a time of use tariff and you wanted to make sure that the battery was not going to discharge until your peak tariff kicked in, then you could set a 0 discharge rate from the start of the day up until your peak tariff starts. Okay, I'll click previous to get back out of that. Alright, so we've talked about the setting up different scenarios, and telling Sunulator what sort of solar system we have for each scenario and what sort of battery. And that's it for the model part of Sunulator. Thank you.